I thank you. Thanks. Yeah, I am absolutely delighted to introduce Dr. Jess McIver today. I think I met Jess when we were both postdocs or grad students and postdocs years ago, and really found her description of all of the goings on of LIGO and gravitational wave science incredibly captivating. So I'm delighted that now Canadians can claim her as their own, so to speak. Jess is a Canada Research Chair in gravitational wave astrophysics, and also has won a host of prizes as part of the LIGO team, and was really instrumental in a ton of work in terms of the instrumentation and analysis. I won't take any more of her time. I'll just remind folks there are a couple of spots left on her schedule for tomorrow, so please make sure to follow us up. I sent a message around, particularly grad students. You'll hear in her talk now, she's very approachable, but it's really fantastic if you want to understand the ins and outs, not just of her science, but also like dealing with collaborations and all of those things that are really important. So without further ado, welcome, Jess.
Thank you. Yeah, thank you so much for having me. And I would love to speak with you, especially grad students and other students. So yes, please do sign up. But I am delighted to tell you about gravitational waves today. So I think it's been a few years since I've been to Toronto. So I wanted to take a broad view of end to end. So what makes gravitational waves? How do we detect them? And then how do we analyze that data? How do we extract that physics from our gravitational wave data? So let's start essentially from the beginning. So gravitational waves are these incredibly weakly interacting ripples in space-time. And this is both an enormous asset in terms of doing astronomy with gravitational waves, and also a great challenge. So it's going to make them incredibly difficult to detect, as we're going to see, because they're so weakly interacting, they're so low amplitude. But it does mean that they can propagate for really vast distances effectively unaltered. So gravitational waves can travel gigaparsecs through dust, through galaxies, through the Earth, and we're still going to get that crystal clear signature of the dynamics of the source that produced them. So we can leverage this to learn quite a lot about the universe. So I'm going to touch on a few of these topics in terms of recent results from the LIGO-Virgo collaboration. But we can use gravitational waves to get this direct probe of the distance of the source to independently measure the rate of expansion of the universe. We can also get insight into incredibly dense matter, so the interior structure of neutron stars. We can use gravitational waves to do these novel probes of general relativity in really extreme space-time curvatures. And of course, now we're starting to see this full picture of what's out there in terms of stellar remnants. All right, so how do you make a gravitational wave? So what you're seeing here, so this is an equation for the gravitational wave strain amplitude, where strain is this stretching and squeezing, this rippling in space-time itself. And I want you to notice three things about this equation. So this space-time strain amplitude is directly proportional to a small number divided by a very, very big number. So already we've got this intuition that this amplitude is going to be incredibly tiny, even for really, really big, massive systems, which does indeed turn out to be true. I'd also like you to notice that this amplitude is proportional to this second time derivative of the quadrupole moment. So what this is telling me is that it's some asymmetric acceleration, some system that has some asymmetry, and we'll see that in order for these to be remotely plausibly detectable, we're going to need those masses to be enormous, so on the scale of stars, and also moving really, really quickly. So we'll see as, for example, two black holes are in their final orbits before they merge together, they're traveling at significant fractions of the speed of light. And then the last thing I want you to notice here is that this space-time strain amplitude is directly proportional to 1 over the distance. And this is different if you're used to doing astronomy with electromagnetic radiation, where usually we've got some kind of an area, we're counting photons with a photodiode maybe, and in that case, the strength of my signal is going to go as 1 over r squared. But here, for gravitational waves, the strength of my signal is going directly as 1 over r. And we're going to see that this is going to allow us to probe really vast distances, especially thinking about taking this census of stellar remnants and doing these mass measurements extra galactically. Okay, so let's say we've got some system. Let's maybe say we've got these two neutron stars that we see here. So they're orbiting around each other, and this is generating, if the orbit is fairly stable, some kind of a semi-sinusoidal signal. So let's say we've got our black hole system. Those black holes are spinning around each other, and this is tracing out this gravitational wave strain pattern. And what this is going to look like for a gravitational wave emitted from the system is, as that gravitational wave passes either into or out of the plane of the screen here, it's going to induce this strain, this relative stretching and squeezing that's characterized by the change in length over length of some 2 points. And you'll notice that if I choose 2 points on this image, and this image is showing me a strain on the order of about 1, but the farther away I choose my 2 points to be, the more confident I can be in my measurements. And you'll also notice that it's this orthogonal motion, this relative stretching and squeezing, where 1 degree of freedom is stretching, the other squeezing. And then we see this cyclic behavior that's going to motivate us to choose this orthogonal shape for our detectors. So my goal now is to try and sense this relative change in distance between some 2 points in space to sense these gravitational waves. And I'm going to choose an interferometer, and I'll walk you through roughly the way that this works. So I've got some input coherent laser light. So I'm shining this laser light into my detector, and then I use a beam splitter to split it in 2 different orthogonal directions. And the way that I've got my detector set up, if there's no relative change in the arms, then my strain signal, so this would be about 0 roughly here, I'm not going to see very much at my output photodiode. However, if I introduce some relative change in length, where I've got some relative change in the length of one arm relative to the other arm, then I'm going to get this induced phase from the different travel time that the light takes to circulate in those 2 arms. So what I'm essentially measuring is this interference pattern, this difference in phase between the light traveling in each arm. That's a result of the slightly different light travel time from this distorted space-time. And I can actually read directly this strain amplitude. So this tells me not only the amplitude of my signal, but also the time frequency morphology of it. So now I'm getting insight into what it is that generated that signal. So let's say I've built this detector. I'm going to make these arms as long as possible, again, to push down the noise and increase my confidence in my measurement here. So we currently have a network of 3 kilometer scale detectors that all have roughly the same shape. And they follow this pattern that we just saw. So you've got some input laser light, you're splitting it in a beam splitter. And now here we're actually going to recycle it so that it actually spends, it makes about 300 cycles on average within these arms. And you can think about it that way, or you can think about it as building up the resonant power of that laser light by about a factor of 300 in those arms. But otherwise, this is operating exactly as we saw in our simple Michelson interferometer, where again, I'm just measuring out this relative change in phase between these kilometer scale arms. And we've got 2 4 kilometer scale detectors in the US. Those are the LIGO detectors. And then 1 3 kilometer scale detector in Italy, that's called the Virgo detector. And we do also have some really important partner detectors around the world. So Geo 600 is a 600 meter prototype that's pioneered a lot of the really foundational technology that we use. There's also Kagra, which is a cryogenic underground detector in Japan that we expect will be coming online, hopefully sometime within the next planned observing run. And then we have LIGO India, which we're hoping to see also online by the end of the decade. So we'll eventually come to have a network of 5 ground-based kilometer scale detectors within the next few years. So it's a pretty exciting time. But let's say we have our detector network, and now our job is to try and recover gravitational waves from our data. So what does this look like? So we can actually leverage the fact that we know these signals are going to be really weakly interacting. So we can use general relativity to predict more or less exactly what the form of that signal is going to look like. So again, I don't expect it to be distorted as it's passing through the universe to get to me. Whatever else it's interacting with, that interaction is going to be weak enough that I don't expect it to have an effect. And I expect that signal to reach me in essentially the same form as it was generated. So we can leverage this really powerful technique called matched filtering, where I know the exact representation of what I expect my signal to look like in time and frequency, and then I'm going to match that against my data. So what you're looking at here, so this is roughly the form of most of these compact binary coalescences, where I've got black holes or neutron stars, and they follow these three stages where they're inspiraling, they're radiating away gravitational waves, and this is spinning up their orbit faster and faster, so increasing that frequency until they merge, and then that final object is going to ring down like a bell. And all of these signals that we've detected to date will have more or less the same structure. This in-spiral phase, where I can treat them as essentially 2 point sources. Then things get a bit interesting when they get close enough together, so right about on the order of the size of the objects, and then this ring down phase. So what I'm going to do is I'm going to simulate a whole bunch of these waveforms, and I'm going to populate what's called a template bank. So I'm going to populate this in what we call the primary mass. So we just arbitrarily define this to be the heavier of the two masses. So you'll see everything populated under this, essentially equal mass line here. And then the secondary mass, which is the lighter of the two. So I am going to populate this so that I am essentially sampling all the parameter space where I expect my detector to be sensitive. So I've got these higher mass boundaries here. So this is related to the lower frequency limit of my detector, which is dominated by ground motion. And then I've also got this differentiation between spin. So I can save a lot of computing power. So each time that I take one of these dots and compare it to my data, that costs me something in terms of computation. So I can reduce the computational cost of my search if I also impose some astrophysically motivated limits. So in addition to sampling in mass, I'm also sampling in spin, which will also change the time frequency evolution of the signal a little bit. And I can say, okay, anything consistent with a neutron star, I'm going to expect that neutron star to be within roughly the spin limits that I see in our own galaxy, which is what you're seeing for the different colors here. These are different spin enforcement constraints. So I can save myself a bit of computation time that way. But what we're going to do is for each and every one of those dots, and there's roughly on the order of 1 million of them, each one of these is a template that has roughly this form with differences based on the mass and the spin of the systems. And I'm going to compare that template with my data. So here we've got some noisy gravitational wave detector data in blue. And I've got my templates, and I've also got this signal, this real signal that's buried in my noise. And what I'm going to do is I'm going to take my template, each one of the 1 million of them, and I'm going to drag that across my noisy data, and I'm going to compute this cross correlation. So this is essentially what's going to give me this signal to noise ratio statistic as the inner product between my template and my data. So let's see what happens. So for each one of my templates, I'm going to be dragging that across my data, and you might notice that this is not an exact match. And this has to do with the sparseness in some places of the template bank we were just looking at, but it doesn't need to be. It needs to be close enough, essentially, so that I'm not missing too much of the power I could recover in this inner product. So our threshold is roughly about 3%. But essentially what I'm looking for is this cross correlation to spike, and this is going to give me a trigger. So now I've got this event candidate I've identified with at least one of my templates. Usually it's going to ring up a whole bunch of them for some real signal. And now my job is to try to decide how significant is this? So how likely is this to be a real event? So now what I can do is I can take this candidate that I just calculated this cross correlation for. So this is going to tell me the signal to noise ratio. And what I can do is for my network of detectors, I can take that cross correlation statistic, that signal to noise ratio, and I can compute this quadrature sum. So this is this network reweighted signal to noise ratio. And what you're seeing here is a network reweighted signal to noise ratio and this blue dashed line for a real event. And now I need to compare the signal to noise ratio for my event candidate to my noise background. And we're going to see this later on, but LIGO and Virgo noise is very ill-behaved. It's non-Gaussian, it's non-stationary, it's full of glitches. So it's incredibly difficult to model. So what I'm going to do is I'm actually going to empirically calculate the rate of chance coincidences of noise. So my goal here again is to try and calculate how likely is it that this candidate would have been generated by chance due to some noise manifestation in my detectors. So what I'm going to do is I'm going to take my real data, and let's say I've got 3 detectors in my network. I'm going to take my data, I'm going to take my event candidates. So I expect to get pings both from glitches and from real signals, where each real signal here is a star, and each glitch you see here is an X. And I'm going to slide that data in time by greater than the gravitational wave travel time or the speed of light travel time between my detectors, which is roughly about 10 milliseconds. So I'll do this for however many detectors I have in my network, and I'm going to recalculate the coincidences. And now when I get coincidences, they must necessarily be due to chance coincidence of glitches, because I have all my real signals that are offset in time now. So I'm empirically measuring the chance of a noise that's going to generate an equivalent signal to noise ratio. So I'm populating these background curves here by doing these time slides. And what I want you to notice here, so if I compare my real candidate event, there she is, hi Science Cat. If I compare this real candidate event signal to noise ratio with these 2 background distributions, I might get a very different significance. So if I understand my noise very well, so this is the grave curve, for example. So if I cut out the parts of my data that I know are very likely to introduce a false positive candidate, then I'm going to do much better in terms of the statistical significance of my candidate event versus if I ignore what I know about my detector. I see a hand up. Please go ahead, Renee.
Hey, Jess, thanks. I just very briefly, so you said the noise is non-stationary and super complicated, but the way you describe it, it's super well understood. But how robust is this kind of procedure to noise it's like unknown unknowns that you haven't modeled?
That's a really great question. So what we do is essentially we're looking at this, we're transforming the data through the lens of our match filter search. So we are counting essentially how many times, how many candidate events we see and what their signal to noise ratio are that are due to glitches. And it's really just the only way that this works is by enforcing that we are not counting gravitational waves coincident with gravitational waves. So it's entirely possible that we are going to get coincidences in here that we don't understand or that are not common noise sources. Some of them, as we'll see later, are common and we do understand them pretty well, but I do expect unknown unknowns to populate this this table. So it's essentially counting everything that's seen through the lens of the match filter search that's contributing to the background.
Thanks.
Yeah, nice question. Okay, so let's say that we're convinced that we've got a significant detection, that if I compare my candidate event signal to noise ratio across my detector network, that it's sufficiently above my background distribution that I'm convinced that it's real. So my next job is to try and figure out what is this. So what we can do, again, is leverage that we know general relativity is going to predict the morphology of the signal. So I can line my model up in phase to get an estimate of masses. And then again, that signal is going to go as 1 over the distance. So once I have that estimate of the masses and I've got that lined up in phase, what I can do is scale my data. And this actually gives me to first order that estimation for the distance. So let's see what this looks like. So I've got some whitened strain data here in blue. And then I've got my model in orange. So this is strain amplitude versus time. So I'm going to evolve my data and let's watch and see what happens. So first I'm changing the phase. So I'm lining it up in phase to get an estimate of the mass. And then once I have that estimate of the mass, I know what the amplitude should be when the signal is generated, and I can scale this model to my data to match my data. And this is going to give me a rough estimate of the distance. So it's not quite so simple in practice. Of course, this is a bit of a cartoon model. So in reality, we actually use Bayesian inference to infer our source properties. And here are some examples. So we've got these posterior distributions of the likelihood that the true value exists within this distribution. And here we have the first 50 or so candidate events. And this is for the primary mass in units of solar mass and the secondary mass in units of solar mass. And they're organized by date here, both in color and also in name. I can also do something similar for the spin. Let's walk through how to read one of these diagrams for a particular event. So this happens to be 1904-12. So the left diagram here, so this is for the primary mass, and this is telling me both about the spin amplitude and also orientation of the spin relative to the orbital angular momentum. So here I've got the primary mass and the secondary mass, and the from 0 to 1 is maximally spinning, and then from 0 degrees to 180 degrees is either aligned with the orbital angular momentum of the system or anti-aligned. And you can see from this one example, even when we can do pretty well with constraining the amplitude of the spin, it's much harder to do this for tilts or how exactly the system, each component of the system is oriented relative to the orbital angular momentum. And it's much, much harder than that to try and infer anything about the secondary mass or the lighter of the two. But how do we do this? So we actually make this really key assumption that we're going to come back to later, which is that our data is a sum of the signals. So this is a signal that's transformed through my detector network. So I see it through the antenna pattern of my system, but it's a sum of the signal plus my detector noise. And we assume when we're constructing this likelihood that when I subtract my signal from my data, that noise is going to be consistent with Gaussian noise. And you may remember that I had just told you that it's not. So this is, or often, very often, this is not the case. So this is something that we devote quite a few person hours to fielding, is how to make this assumption as valid as we can. But what have we seen so far, assuming that this process has all worked as it should, and we've got these estimates of mass and estimates of spin. So what are we learning? So this is a schematic. So this is showing results from up to the first half of the third observing run. So this is up to September of 2019. And the y-axis here is mass in units of solar masses, and the x-axis has no real meaning whatsoever, but the colors do. So what this is showing you is masses of stellar remnants that are estimated either with electromagnetic radiation. So this is the yellow dots and the purple dots for black holes. So black holes and X-ray binaries. And then the orange dots are neutron star masses estimated with gravitational waves. And then the blue dots here are black holes estimated with gravitational waves. And you'll notice that each one of these is a triple system. So you'll have the two component masses that are measured, and then the mass of the final product of the merger. And what it's really hard to see here is that not only are we unveiling this new regime in black hole masses that this wasn't visible to us with electromagnetic radiation, but we're also probing these enormous distances relative to what we can measure electromagnetically. So I'm going to show you a similar plot with all of the same points in it, but now with this added axis of distance. So this is again mass and solar masses. And now we've got these events all plotted on this distance scale as well. So now the colors are neutron stars with masses estimated electromagnetically. Green is black holes estimated electromagnetically. And you'll notice that these go just a little bit beyond the edge of our own galaxy. Whereas gravitational waves, we don't actually start observing until beyond the Virgo cluster. And some of these are, at least a few, I think our highest to date was over 5 gigaparsecs away. And again, each one of these will come in these sets of 3, the 2 component masses and then the final mass. So we're really sampling this very distinct population, both in mass and then also in distance. And now I always love to talk about the new results. So these are from just this past November. We released our latest catalog. So this is GWTC3. So this is including data from the 2 LIGO detectors, the Virgo detector, and spanning November 2019 up to when we had to end the run a little bit early due to the pandemic. So we had 39 new confident detections, bringing the total up to 90. And you may remember that not even 6 years ago, this was barely 1 or 2. So it's been a very fast moving period of developments for the fields. But this is our schematic now. So it looks like there's a pattern here just because it's getting so hard to fit everything on the same slide, which is a nice problem to have. But again, it's mass and solar masses now, and no particular meaning on the x-axis. But you can see here now, gravitational waves are really starting to dominate what we know about the measured masses of these stellar remnants, especially for black holes. And we're also probing these new regimes in mass. So for example, here is the first definitive measurements of an intermediate mass black hole, where this final object was really firmly above about 100 solar masses, and then very likely something like about 160 solar masses. So what can we infer from this? So let's say we've got this measured distribution of masses and spins. So one thing we can get insight into is how these systems are formed. So it's not a trivial problem to think about how we would get, let's say, 2 stars that are born, that die, that form a binary somehow, either together or separately, and then actually get close enough to be able to radiate away gravitational wave energy quickly enough to merge within a Hubble time. It's a non-trivial problem. So here are some examples of possible formation mechanisms where we expect to eventually see signatures from gravitational waves that'll give us clues as to how they formed. So one is this isolated evolution, where you've got 2 stars that are born together, that die together, that have some kind of a mechanism for getting them close together. So for example, a common envelope that would bring them very close in their orbit. And for these systems, what you'd expect to see is the tendency towards spins that are aligned, or roughly aligned, modulo some kind of a supernova kick, with this orbital angular momentum of the system. And you'd also expect maybe potentially some other signs, such as masses falling within a range of likely masses for stellar formation. So for example, not an intermediate mass black hole. And then also the eccentricity of the orbit, you would expect to see very, very close to circularize. Whereas, let's say you have 2 black holes out in the wild, maybe in a globular cluster, some kind of a really dense, active, dynamic environment, where you might see capture and then merger. And so for those types of systems, you'd expect to see this isotropic distribution of spins, and then potentially also eccentricity, and maybe in the case of hierarchical mergers, where you have the product of a previous merger merging, you might also start to see some signatures in terms of where the masses of those systems. So those are the types of signatures you might see. So focusing on spin, something that I wanted to point out is, so here's an example of this most recent catalog. These are 6 different events, and what I want you to take away from this is more evidence that even when we can constrain the spin in amplitude, it's really pretty difficult for us to do this also with tilt. So for example, here's an event that we have constrained that's likely spinning pretty quickly, at least this primary mass, the heavier of the 2. but it's difficult to tell where exactly the object is aligned, except that it's more likely to be anti-aligned with the system than aligned, and that's in terms of orbital angular momentum. So I want to tell you briefly about a neat project that a current PhD and former master's student of mine did, showing how much better we expect to be able to do both with this spin amplitude and also the tilt angle measurements. So what you're seeing here, each one of these points is for a system with some mass ratio, so the difference in masses between the two systems, and some amplitude of injected spin from 0 to pretty near maximal. And this is the width of the posterior, so both for the spin amplitude and for the measured tilt. And the summary is that if you compare how much better you're going to do with this near future version of the LIGO detectors called A+, which we hope to be online within the next 2 to 3 years, you actually end up doing on average about 50% better in terms of your ability to constrain the spin both in amplitude and in tilt. So that's pretty exciting in terms of being able to better distinguish between these formation mechanisms. But we're also starting to see some patterns in terms of mass. So here are some highlights from this companion paper to this third catalog. So we're getting more information about the merger rates of different systems. So this is 2 neutron stars, a neutron star and a black hole, and 2 black holes. But what I want to draw your attention to, so this is the distribution in terms of primary mass and secondary mass. And so we've got these diagonal lines here to kind of guide your eye in terms of the mass ratio of the system, where this is 1. And you can see that there's a population that's sort of hovering a little bit below 1, but roughly equal mass. But then there's also a different population that's starting to populate where the masses are more than a factor of 2 difference. And these are systems where it's going to be easier for us to disentangle parameters that are degenerate in our Bayesian analysis. So if you have a higher mass ratio, this is going to make it easier to detect those higher order harmonics and distinguish potentially different spins as well. All right, so something else I want to point out from the same paper. So this is our companion paper thinking about the populations that are in the data. So we can actually infer neutron star masses and compare that to these galactic neutron star masses that are measured. So from the few gravitational wave events we have observed so far, so what you're looking at is this probability versus the value of the neutron star mass. And there are 2 different distributions here. So a power law model and a peak model, just different models used to fit the data. And then also for reference is the prior, which is the dashed line, and then the galactic distribution here in this solid black line. So you can see here we're seeing some slight differences in terms of the masses of neutron stars measured extragalactically with gravitational waves versus galactically with electromagnetic radiation. And then there's also an interesting inset here. So this is the probability of the maximum mass of the neutron star, where for the galactic distribution, we've got a measurement or 2 that's pulling that probability up for these higher masses. But measured with gravitational waves, both of these models are showing that it's the median is just a little bit less than 2 for this maximum neutron star mass. And thinking more about black holes, so this is looking at the inferred primary mass distribution for binary black holes. So this is in terms of rate, so normalized to gigaparsecs cubed in years. This is normalized to rate. So what we're seeing is we've got these really the strong peak here and potentially a secondary peak related to what we think we know about stellar evolution. So we are starting to see some features that have pretty interesting implications in terms of potentially eventually being able to infer redshift directly from gravitational waves. So you could think about once you know where these peaks are in reality in your distribution, doing something like mass spectroscopy, where you're seeing how those masses are redshifted with distance and using that to infer redshift in addition to directly inferring distance. So that's pretty exciting for the near future. And speaking of cosmology, there was also a companion paper on how much better we could do with independent measurements of the Hubble constant, where we are still getting redshift from electromagnetic observations. It's just the distance here that's coming from gravitational waves. But to give you a tour, so here's the probability that the Hubble constant has some value, and then for reference is both the cosmic microwave background and supernovae measurements. So we're still not doing very well here with GW 170817. So this is the binary neutron star merger, which you can also see here, the reference for the initial measurement alone in black. But if we add to this a statistical measure of the measured distance of binary black hole sources plus galaxy catalogs where we have information, statistically speaking, about the average redshifts in those localized volumes, we can form this, this blue curve here, which is shifted a little bit more towards the cosmic microwave background measurement, but still is perfectly consistent with both. So hopefully on the order of the next 5 or so years, we'll start to see more differentiating power from gravitational waves. And again, here in terms of measurement of the Hubble constant as a function of redshift, so we're still not able to probe either very far in redshift or reduce our uncertainties. So it's especially for leveraging binary black holes without a clear electromagnetic counterpart in host galaxy, that'll take on the order of roughly hundreds more measurements for us to start to reduce that down and make some interesting observations about potential dependence on the Hubble constants versus redshift. Okay, so this is quite a lot of recent results. So we are learning some things. The prospects for us to learn even more in the near future are pretty astonishing. But how exactly do we get there? So I do want to take you on a tour of the detectors. So this is LIGO Hanford from the sky, and this is actually 2 kilometers, not 4. You're only seeing about half the arm so far. But what we're going to do is we're going to do a fly through of the laser light, and we're actually going to see in practice a bit more detail in terms of how these detectors work and how the measurements are made. So we're going to start from our laser light. So this is our input pre-stabilized laser, and this is going to get steered into a 3-optic cavity in this pink purple color here. This is called the input mode cleaner. And what it does is it selects for this Gaussian spatial beam profile. And then the beam is steered into another 3-optic cavity here in this yellow-green color. This is called the power recycling cavity. What it will do is recycle light that exits the beam splitter back into the beam splitter. But for now, the light passes straight to the beam splitter, and we're going to see that it's split 50% in each direction, exactly as we saw before in our simple interferometer scheme. So this light is going to travel down each one of the arms, which are lined with these 2 parallel optics, and this forms what we call a Fabry-Perot cavity. And we mentioned a bit earlier that this is actually going to cycle the light up by a factor of about 300. So we can start with an input power of roughly on the order of 180 or so watts, and cycle this up to roughly about a megawatt that's resonant in the arms. So zooming all the way down 4 kilometers away to the end station, we get this glimpse of one of these test mass optics, which forms the arms of the detector. So they weigh roughly about 90 pounds. They're about this big or so. And as the light finishes its journey, so it's recombined at the beam splitter, 50% of it is going to travel back towards the power recycling cavity and be recycled, and then the other 50% will travel to the signal recycling cavity, which serves a similar purpose. And then finally, it's going to make its way to this bow tie cavity here. That's the output mode cleaner, which serves a similar purpose to the input mode cleaner, and then to our photodiode. So just getting a picture of how this works in practice. So this is showing you a gravitational wave traveling into or out of the plane of the detector. This induces this relative stretching and squeezing. And this is actually what we would see in terms of the resonant light within the detector. And this photodiode is going to register this amplitude of our signal versus time. And what you can see here is tracing out the data from the very first gravitational wave detection. So I want to spend just a little bit of time on noise. So I had some really interesting conversations earlier, people remembering all the previous observing runs, we used to call them science runs, of LIGO before it was Advanced LIGO, of pushing down that noise floor more and more. So I want to tell you about this technology that got us here. So this is the strain noise amplitude for LIGO Livingston and its Advanced LIGO configuration versus frequency. And you'll notice that all gravitational wave detectors, including LISA, have the same basic sort of structure, where you've got low frequency noise that's essentially this real physical motion that displaces the optics that you're using to make the measurement relative to each other. So for Advanced LIGO, this is seismic noise. For LISA, this is the micronewton thrusters. And then as you get to higher frequencies, you start to see this sweep and then increase in noise. And this is dominated by quantum noise. So right now, the Advanced LIGO detectors are fully quantum limited above roughly about 60 or so hertz. And what this means is that we're limited by this shot noise. So we're essentially in the business of counting photons. And like any counting experiment, your noise is going to go as 1 over the square root of whatever it is you're counting. So what we want to do is increase the power, the number of photons that are cycling in our detector arms. And there are 2 ways we can do that. So one is by inputting more power. So this is a snapshot of our pre-stabilized laser, which will eventually get up to about 180 watts. Another is recycling. So we saw all those strategic recycling cavities that are going to cycle that power up. And then something that I don't think I quite have enough time to talk about today, but you can also sort of cheat the quantum limit and perform what's called squeezing, which is something that was implemented in the last observing run, and we expect to leverage even more in the future. But eventually we're going to come to rest right on the thermal limits, which is going to be dominated by the Brownian motion of our optical coatings. And just again, give you a sense of scale, this is real displacement that's interfering with our relative distance measurements of the optic that's 4 kilometers away. And the last thing that I want to mention, so I would say that it's this technology here, which is really one of the primary reasons that we're able to measure gravitational waves now, where we weren't, say, 10 years ago. So this is an active seismic isolation system. And essentially what it does is it measures the input ground motion and predicts how the instrumentation that's holding those optics is going to respond, and then pushes on it to cancel it out. And we have actually gained in this really critical region, roughly about 50 hertz, several orders of magnitude and improvement in our sensitivity thanks to this technology. And this is right where we see those binary black holes signals sweeping through. So it's not so much of a surprise that we're suddenly able to make detections where we weren't before. But overall, what does this buy us? So here is a real snapshot of our sensitivity. So we start by zooming out around the electron, around a hydrogen atom. We're going to zoom all the way into the proton, and I'm going to show you to scale what the relative displacement measurement is for the LIGO detectors. So it's about 10,000 times smaller than the diameter of a proton, and we're actually doing about roughly 2 or so times better than we did when this animation was made back in 2016. So it may not surprise you at all to learn that such a sensitive instrument is actually really prone to lots of other noise. So let's see, I'm running a little bit low on time, so I think what I'm going to do is give you the lightning tour of noise. So this is especially relevant to people who are thinking about electromagnetic follow-up. But what you're seeing is a rate of glitches in the 2 LIGO detectors over O3b. And you can see that there are some really big excursions here. These have to do with a source of glitches called scattered light. So there are 2 different forms of this. I won't go into the physics of it unless you would like me. Please ask me about it later if you're interested in light scattering. It's a really neat physics problem. But essentially, we were able to mitigate this with an instrument change pretty well in Hanford, which is dominated by this slow scattering. So this is a longer duration kind of glitch, which is going to catch lower mass sources like binary neutron stars. It's going to be more problematic for those types of searches. Whereas fast scattering, so this is a modulation of light scattering, is what's dominant at LIGO Livingston, where the same change didn't help so much. This is still tracking roughly with the weather. So you're going to get increases in glitching, especially light scattering from ocean waves, from nearby storms, from earthquakes, even distant ones. And I want to give you a sense of what this looks like over the course of the day. So this is an example of a LIGO detector that's struggling with some kind of seismic noise. And what tells me that is two things. So one is these periods of missing data, which tells me that it's having trouble maintaining that light resonance. So we would call this lock. I'm having trouble keeping my detector locked. That's one clue. And another one is all these dots above roughly 20 hertz. And what each one of these are is each is a scattered light glitch that can rise right up into this really interesting frequency regime for gravitational wave signals, where I might expect a binary black hole to sweep up roughly about here in frequency. And what I want you to notice is just how frequent these are. So it's really every other second that we're seeing these when ground motion is high. And this can cause a much higher rate of false positive alerts that we later have to retract. So I'll maybe mention just one example before moving on to the future. So this is maybe one of our more famous examples. So this is our first actually successful automated alert that we issued back at the beginning of the previous observing run. So this is May 18th, 2019. And it looked really great at first. So it was localized to about 10 megaparsecs closer than 170817, the first multi-messenger detection. It's got this pretty high probability that it contains a neutron star. The sky map is all really nice and localized. However, it was actually a glitch. So this is an earthquake here that our our system at the time had a lot of trouble identifying because it's so long. So I was showing you these examples of glitches earlier that are roughly about on the order of a second or less, whereas this is going on for tens of seconds and really deeply confused the search for neutron stars. So I think I'm going to skip over a couple of really super neat machine learning applications that a former postdoc of mine, Miriam Cabrero, has done that we hope will be really helpful for addressing exactly this problem. It looks really promising. But what I want to mention is that as we come back online with a slightly higher sensitivity, we're going to expect this rate of events to balloon. So what we expect to see is that even for a very small change in sensitivity, as we're pushing that noise floor down, we get that factor of distance, of reach, cubed in terms of volume. So we really expect that rate to sweep way up. So for reference, here in red is where we were for the last observing run, at least for Hanford. So Livingston is here in green. And then both of those detectors are targeting this gray curve here for 04. So this is where we hope to be for the next observing run, which if we make it and we understand the true astrophysical rates well enough, should take us from roughly about a signal per week in the last observing run to a confirmed gold-plated detection per day, plus a whole bunch of other candidates that are very likely noise. So our rate is about to turn into a fire hose for our next observing run, and even more so beyond that. And what might we detect with our current detectors? So without going into space or building new facilities, we could already see some really pretty interesting things we haven't seen yet. So this is some explored region of parameter space where this y-axis is telling me how well can I model this source, and the x-axis is telling me how long in duration it is. So we hope very much to get lucky, maybe with a core collapse supernova in our own galaxy. And we really do expect to see semi-sinusoidal gravitational waves from spinning neutron stars in our own galaxy. And this would tell us quite a lot about the neutron star equation of state, to the point that if we don't start to observe them in near future data, this is already telling us something pretty interesting about the allowed asymmetry of the neutron star crust. And then I think I'd like to leave you with just a quick snapshot of all these other exciting experiments that are coming online. So gamma ray satellites, space missions, ground-based missions that are really exciting, and all these different multi-messenger and wavelength bands that are going to be coincident with these ground-based detectors, this network of 5, plus these upgrades that we were talking about. And then even looking beyond that, so to the next decade, potentially these future ground-based detectors and also space-based gravitational wave missions, which will give us totally different bands and open up our sensitivity to things like supermassive black holes. Okay, with that, I think we're right on the hour here. So I'm very happy to take any questions people might have, and thanks very much for your time.
Thanks so much, Jess. That was great. Really, really interesting. Yeah, we are at the hour, but I think we can take a couple of questions if folks are around and would like to raise their hands. Bob.
So hold on to your hats, because this is going to be a weird one. Because while you were giving your talk, I was like, this is amazing. This is the coolest thing I've ever seen. And I've had that experience with other LIGO talks. And so I was like, I wonder what this thing cost us. And so according to Professor Google, it was only $1.1 billion, which is actually, you know, that's less than TMT. That's, you know, one, tenth what JWST is going to cost. So I was like, it is what a deal, you know, over 40 years, $1 billion. And so what do we do next? You know, if I gave you, if I was like, Jess, here's a check for, $3 billion, what would you do next, right? Because I don't know, would you, put, LIGOs all over the planet like candy? You probably could do it cheap now, right? Having done it once or 3 times. What would you do next?
That is an excellent question. So I'm really pleased that you noticed that number is integrated over 40 years, because yeah, it's all of the baseline technology developments, all of, from the ground up, essentially, to develop this idea from first principles all the way to where we are now. But okay, so let's see. I wonder if I've actually thrown in some slides here about next generation detectors. So let's assume that LISA's going to happen, and NASA and ESA don't need me to give them money, and yeah, that's gonna fly and be really wonderful. Well, shoot, I don't think I didn't include them here, but what I would do is I would build a network of 3 10-kilometer scale detectors. And what that would get me is I would be able to sense gravitational waves, at least from stellar mass black holes, all the way out to the dawn of cosmic time. I would see everything. And I would not put them all in the Northern Hemisphere. We learned our lesson. And there are actually plans to do this. So there's a European-based design called Einstein Telescope, which is 10 kilometers in a LISA configuration. So what the triangle gets you is you don't need confirmation from other detectors for some cases in noise, but also you get essentially sensitivity to the entire sky at the cost of lowering your maximum sensitivity. So that's a choice you can make. That's what Einstein Telescope is doing. There's also the US-based design called the Cosmic Explorer, which is up to 40 kilometers long, and it's also scalable. But even though we have a really good handle on the technology and we could absolutely manufacture most of those components pretty cheaply, it's going to be dominated by just moving dirt. That's the dominant cost, because the baselines are long enough now that you would need to find a natural bowl in order to shoot your laser straight for 40 kilometers, or you have to dig pretty, not that far. I mean, it's certainly not, you wouldn't need to, do a snow lab or Kamiokande or anything. It's only on the order of 10 meters or so, but we will be looking at costs of construction dominating next generation.
Thanks.
Thanks, Jess. Well, hopefully you'll be around to lead all of this. So I think folks will have to leave to attend other classes, but just a reminder, please sign up. There are a couple of sessions left to speak with Jess tomorrow, and let's thank her again. Thanks so much, Jess. And I'm seeing you at 4 p.m.
Excellent.
Okay. Thanks a lot. Cheers, folks.
Yeah, thanks everybody.
Bye.